In this lecture, we are going to look at design for manufacturability. So design for manufacturability, or DFM in short, is a very broad area. Right? So as the name suggests, you have to design for manufacturing, right? Either manufacturing or manufacturability, these two are interchangeable. So the whole idea in DFM is to understand the manufacturing process and then apply the limitation of the manufacturing process in the design phase itself. So initially, design and manufacturing was two different entities. So designer never interacted with manufacturing units. So whatever you design, you expect those design to turn out to be as good as possible, right? But then you relied on the manufacturer to give you whatever you desired. But more often, there are certain limitations, right, in manufacturing itself. So there are variabilities, and there are some dimensions and some specifications that may or may not be achievable in manufacturing. So there was a big misunderstanding between these two that resulted in waste of resource more often. This also happens in research these days. So when you are doing development of a certain device or circuit, you should always keep in mind, how are we going to fabricate this? If this device or circuit cannot be fabricated, use the existing methods or whatever technology that you are going to use, then there is very little scope in exploring the applicability of the device or circuits that you are developing. So it is very important to understand whether your designs can be manufactured, right, or fabricated, taking into account all the non-uniformities and variabilities that one would encounter in manufacturing. So ideally, as a designer, you design a circuit and you say, this is the line width, and this is the gap width, and this is the resistivity I want, and this is the doping concentration I want, and you have done a very good simulation platform that is telling you that this is going to be the best device that you can get. But then if you can't achieve all those specifications, then it doesn't matter whether it's best device in simulation. And if you can't fabricate, there is no usefulness in having such a design, right? It just remains as a design. You cannot realize it. If you want to realize such a spectacular device, then we should understand the manufacturing limitations and the variabilities, so that you can incorporate those in your design stage and achieve devices and circuits that can yield better results, right? So in this lecture, we are going to look at the overview of design for manufacturability. So the topic itself is pretty broad. You can use DFM for mechanical manufacturing, DFM for computer science, you can use DFM for microelectronics, and DFM for chemical plants and chemical engineering. So the applications are varied, okay, but there are some underlying ideas that is fundamental to the field that you are going to apply, right? So in this lecture, we will not go deep into any specific field, but we will try to understand the underlying principle and what one need to be aware while understanding the design when it comes to manufacturing. So the first thing that comes to mind when you are looking at DFM is variability. The whole idea of a design for manufacturability is because of variabilities that you get during fabrication process, right? So you design or a device or a circuit that should give you a typical characteristic, right? So that is what you are expecting. But then when you get the device, it may not give you the typical characteristic that you are actually expecting, right? And similarly, you might have multiple devices, multiple circuits that should have identical behavior, and you designed it identical, let's say, right, in your layout. You can do copy pasting. Let's say I have just copy pasted one block to the other die, But then when you get these devices after fabrication, then you find out that they are not identical after fabrication. So this is all coming from variability during the manufacturing process. And then there are two type of variability or variation. One is systematic, right, and the other one is random, right. The systematic, as name suggests, it is deterministic variability. So due to an identifiable source that could be compensated, right, is very important. We will reiterate this again and again. Systematic variations are variation that could be traced. Okay, so you should be able to find the source of this variation, and also we should be able to apply some compensation methods in order to counter the systematic variation. On the other hand, we have random variation. So random variations are the fluctuation that happens at the microscopic scale, and they are statistical in nature, and there is no way to completely avoid this random variation, right. You might be able to identify this is the source, but the source itself could be uncontrollable. So it is very hard to completely avoid this random variation. However, you should be aware of this variation that exists in your fabrication process. And the variability could be classified in different ways, right, as I mentioned, systematic and random. And this is the scale, right. It could be intra-die or inter-die, and the random variation could also be intra-die or inter-die. So the die here means just the chip, right. So if you take a wafer, and then you can have multiple chips inside this footprint, and each of this chip is called a die, right, a chip or a die. And the intra meaning within the die variation, systematic or random, and then you also have a random variation either within the die or between the dies, right. So how do we address these problems, right? So these problems can be addressed by looking at the manufacturability, right, of your design. So whether my design fits into the manufacturing protocols. You can do simulations. So by taking the manufacturing protocol, looking at what is the width window that I have and what is the height variation that one could have, right, and then for instance the resistivity variation that one could have, right. All these things could be used to do corner simulation. So if my width variation is within this window, how is my device going to behave? And then you could do a statistical design. This is primarily for random variation. So whether my random variation follows a Gaussian spectrum, or this is a completely a normal distribution, or undetermined. So there are multiple ways to take the data of this random distribution, and then you can model it either through Monte Carlo or any other simulation in order to look at how my device performance is going to be affected, right, for all these random and systematic variation. And the next thing is defects. Variability is slightly different from defects. Defects are can be originated from hard rules. That means if you have violated a design rule, then it becomes a defect. And also there are few recommended rules which may or may not be affecting your performance, but this is also a defect in a conventional sense. So you should be aware of the design rules, right, and also what are all the mild rules, right. So whether that mild rules become hard for your design, right. So the mild rules could be for the process, but if that mild rule is becoming a hard rule for your design, then it becomes a hard defect. So in order to understand that, you should do a critical area analysis, right. If this is my area, if these rules apply, then whether my chip or the circuit area will be affected, and also you look at the yields of your circuit or your device based on these defects, right. So the variability can affect at various scales, right? In the last slide I mentioned something about inter-die and intra-die. So this is just an intra-die. You take a single chip and the variability could be within that chip. So you might have two amplifiers designed on the same die, but then these two amplifiers are behaving slightly different. The gains are slightly different, the threshold voltages are slightly different. So this variability could be within the die, right? Between the dies also it is possible, right? So within a wafer you have intra-die variation, right? And this could be spatial variation because this wafer is processed at a particular time t, right? So there is no time lag between the two dies because this is a parallel processing, and this is again everything is done at t0, let's say, right? But this is all spatial variation only. But then if you go from wafer to wafer, so this wafer was done at t0 and this was done at t0 plus delta t. So now you have both spatial variation and also temporal variation. So what is the meaning of temporal variation? So spatial variation we understand, right? Any non-uniformity on the substrate with respect to distance or position, right? The temporal variation is difference in time. I process one wafer now and after 10 minutes I am processing another wafer, but at the same process. But between T0 and T1, few things might have changed. For example, the temperature of the chamber might have changed, or temperature of the environment, or temperature of the wet chemical that you are using. So there could be some change, right? Or the environment could have changed. So this will also affect your variability. So wafer to wafer, batch to batch, a group of wafer is called a batch, okay? And the number of wafers depends on fabrication unit, so it can be anywhere from 5 to 50, right, as a single batch. So within the batch you might have some variability, but batch to batch you will also have variability. So this is where you have both spatial variation and also you have temporal variation. So the variability becomes more harder and harder to mitigate. So I'm just trying to capture just two processes, right? One is wafer, the other one is lithography, and the other one is etch, right? So let's look at what are all the possible things that can go wrong or that can create variability. And if you look at it, everything that goes into the processing can induce variability. Just to give you an example, so you take a mask, right? So the mask flatness could give you some variability. Ideally you expect the mask to be flat. If the mask is not really flat, if there are some bow in the wafer or bow in the mask, then your diffraction is going to be slightly different, and the transmission variation can also result in variability. And let's look at litho tool itself, right? So your exposure dose could vary, right? Your chuck flatness, right, your chuck that is holding your wafer, there could be focus instability, right, and there could be source spectrum slightly shifting. Resist process could have variability, and then the wafer itself, right, we'll see in few slides how this wafer is also affecting, right, the wafer flatness. If the wafer is not flat, this is again going to affect your focus, right? And similarly stack uniformity. If I have multiple layers, right, this is oxide, and then say this is silicon, and then maybe I have silicon nitride. Any thickness non-uniformity in these layers can result in reflection issues and also resulting in non-uniformity. In the etch process, this is something we also saw earlier, any change in the bias voltage, temperature, resist coverage, this is the density dependent issue, the chemistry, right, if the chemicals are not mixed properly, if there is any density variation of these radicals within the plasma, will also give rise to variability, right, in terms of line width or etch depth, everything. So when you process a wafer, whatever parameters that dictates that process are responsible for this variability. And this is just an example of thickness variation, right? So how thickness variation could affect your processing. So this is number of wafers, and this is within wafer what is the variation, right? And this is 3 sigma. So you can look at between wafers you have a variation as well, right? And within wafer there is a variation. For instance, here the mean is somewhere here, right? So but you see the distribution, there is a pretty large distribution around the mean, and then the 3 sigma also, right? The standard deviation of the thickness also around 4 nanometer, but some are very good wafers with very low variation, and some are also very high, right? So these intrinsic thickness variation can also contribute. So for instance, within a wafer you could have 3% variation in thickness, and wafer to wafer can be better, it can be 1.9% variation, right? So one need to be aware of this variability. If you are going to process large number of samples, right, between the sample am I having uniform thickness, uniform coating, so this dictates your end result. So when you are buying a wafer from an external vendor, so the specification is given by the vendor, so you don't have much control over the uniformity, right? But over time, I think in generation after generation, the thickness uniformity is also improving, which is something very good, but you need to be aware that there is a thickness variation, right? And which may or may not affect your design based on your critical nature of your design with respect to thickness. If your thickness variation is 1 nanometer and then your device won't work, then you may want to re-look at your design, because here you see you have a range of about 4 or 5 nanometers, right? So if the thickness variation is 4 nanometer, you should make sure your design can accommodate this 4 nanometer variation, because you don't know where this device is going to sit on the wafer, right? Whether my device will sit on the part which is 218 nanometer or it is going to sit on 220 nanometer, right? So there is a 2 nanometer variation already. So whether you will be able to support this sort of variation or not is a critical question that one need to answer. And the next thing is again related to litho, exposure itself, right? So we know when you change the exposure dose, your line width changes. So let's look at the stepper and scanner example. So in the illumination option, if it is a stepper, you have a flood illumination of your structure, but in a scanner you have a thin slit, right, that is illuminating. But the assumption here is this slit has uniform illumination or uniform intensity, but in reality you don't have that uniformity. You will have a certain change in the intensity profile going from left to right in your slit, right? And this variation, right, this delta E is something that you should be aware of. And how this is going to affect? So if I take a simple die here and then I'm scanning this slit, right, and this slit is going to give you a certain dose over this wafer. And because of this slit scanning across, if I have identical devices in these points that are marked cross, if I measure all these devices, they are not going to give me a same response as I expect, because at the center I have a certain dose and at the edge I have a different dose. And because of this variation in the intensity exposure dose, you will have slight variation in CD, and this is what you want to reduce also. This is something we saw in lithography also, what we call exposure latitude, right? And here just to give you an example, so 1% change in the exposure dose could result in a 1.3 nanometer change in the critical dimension, right? This is for highly controlled system. But if your system is not really tuned and controlled, then you can expect this delta CD to be much larger. Okay. So you need to be aware of this non-uniformity in the intensity can also cause variability there. So the systematic effects can be traced back, right? And that is something that we can compensate, and that is very important. The variability, we only call variability is systematic if we can understand the origin and model the effect for compensation. If we can identify and then if we cannot model the effect, then it becomes random issue. Okay. So if it is systematic, we should be able to identify, not just identify, we should be able to understand the origin and also compensate it. Okay. And this, what kind of failures are systematic? We should first look at the effect, right? When you look at it for the first time, it will look random because you haven't encountered it, right? So you have to run multiple tests, right? Multiple experiments, and then you examine the data, and then you will see that this random nature is not random, it is actually systematic. So now a one-off experiment that could have resulted in conclusion of a random effect. So now repeated measurements can give you a clear indication that it is not random, it is systematic. So one should understand that. So understanding the effect or understanding and identifying the effect is the first step towards improvement, right? Once you understand and identify the effect, then you attack the problem, right? So we should not blindly see that, oh, I have particles and then I start cleaning, right? So the particle defects are because of some source. Identify the source and annihilate the source. If you just start cleaning the wafer and then say my wafer is clean, now I can proceed, but your next wafer will also have particles. So how are you going to address that problems, right? It becomes resource heavy if you don't address the problem. So that is the reason why understanding the problem, right, and identifying the effects are the primary steps in addressing the variability. So the variability could be optical proximity effect, which needs thorough investigation, and also you could have thickness non-uniformity during deposition, and this is a plasma process or CVD process where your flows are not proper, your wafer placement might be off. So all this could result in variability. So once you encounter a variability because of deposition, the best thing to do is to look at what is the process that I am running, whether the process in itself is outside the process window or not, and then you can address the variability. And variability in thickness because of chemical mechanical polishing, right? This is again an example of polishing the wafer, but then you could have local variability and global variability in thicknesses. This could be either from the process or this could be from the design itself. So we need to first understand the origin of it and then address the problem. So this becomes a systematic understanding of the problems that you encounter. So this variability also affects yield, right? This is a very important point. Variability in dimension or any other design parameter impacts the device performance, right? So this is all known. So this is not new, right? So whether this impact is terminal or not is the question, right? So when you are looking at variability, we should use that variability during the design phase itself. As I mentioned, one should do a corner analysis, right? You take parameter x and y that is going to affect your device performance, and then you run the window for x and then you run a window for y, and then look at the performance of this device, whether the figure of merit of this particular device is within spec or not. So if it is not within spec, then you have to redesign this because the process window that you have is hard, right? So Either you request the foundry or the fabrication facility to tune the process to get better process window, or you have to redesign. More often you will be given a window, because re-optimization is an expensive process. Probably they have done the best to give you the window that you can use for better yield, but if your device is not yielding within that window, it's better to go back to the design board and design to the window that you got from the fabrication facility. So you need to do two things. One is functional yield analysis and then parametric yield analysis. So functional yield is either it is working or not, there is a complete failure of device or a circuit, right? So we need to look at whether these kind of variability or defect is going to completely kill my device or circuit. And then you need to also look at the parametric yield. That means my device is still working, but it is out of spec or it is working suboptimal. So in that case also you need to do an analysis of these three important factors. Process, right? What is the process variation? What about the supply variation? This could be voltage variation or input power, right, variation, and then the environmental variation. What happens if the temperature varies? Mostly you do this analysis, right? As a designer you will do supply and environmental variation, you do temperature variation, and then you do supply voltage variation, but then you should also do process variation as well, because when the process variation happens, you are going to have change in your line width, right? It could be height or it could be the material itself, right? So your resistivity or conductivity of the material could also change. So we need to incorporate all of these parameters to look at parametric yield. So the variability of the device also, or the circuit, has a direct implication on the reliability of your circuit or the device, right? So when you have a defect and then it is marginally passes, right? It's marginally passed during the test, but then this is a reliability concern for you over time, right? So the defect that you identified could grow over time, and then it can cause failure. And if this happens, then you know your customer won't be happy, and also when you are running long term measurement, if it fails, then you have to redo that experiment again, right? So you should take care of this defects, right? Whether these defects could grow in time. If these defects can grow over time, you may want to address this defects, right? Don't let it pass. So what you can do is you can reduce the quality metric window, right? You say I have a distribution and then I can tighten the distribution now, right? When you tighten the distribution and say only I will allow devices with this certain metric, then that will give you better reliability, but that is going to increase the unit cost, because the devices that are outside the window, who is going to pay for it, right? You have to take those costs into account while you are costing for your device that you are going to sell, and also it will result in a loss of revenue. Okay, so one need to be careful about putting the right window, quality metric window, and the defect analysis here. So addressing defects are one of the important thing than working towards quality metrics, right? So in order to understand this, you need to do a thorough a test flow, right? So you have to test the device properly, right? Whenever you get a wafer or a device made, right? And build devices that are robust to defect and variability, right? So this is very important. This is like a feedback. So you make the first batch and then you feed back to the designer. This is what is required in terms of design. So the defect and yield data is highly confidential. You are not going to get these details from your fabrication facility or any manufacturing facility, but you get this process design kit, PDKs, that you can use, and these PDK document will have this support design data to help you in understanding the yield and defect right? But this is all encrypted, so there is no need to look at the data, but this encrypted file will have all those details in order to run the corner simulations and so on. And the next thing is about the die size, right? The defects and are going to affect your yield. So there are two images here, left and right. Both are of same size wafer, but the only thing is difference in the die size, right? On the left side you have smaller dies, on the right side you have larger dies, but the defect density remains the same, right? In this case I have used the same defect, but on the left side you have more number of dies coming out, on the right side you have few number of dies. Alright, so this should also give you an idea, right? If I reduce the size of my dies, I will get more number of dies out, right? So this could be an inference from this image, but you should also look at, you know, die to die variability as well, right? Which is something that is also affect your uniformity when you are building a system using these two dies. Okay, so it is all about restricting your defect distribution, and in some cases you may not be able to reduce the size of your dies also, right? So the die size is primarily dictated by application and technology limitation. You may not be able to, you know, make smaller than possible. So in summary, initially design used to be separately done, but now design and manufacturing is put into in a single process. So design is now part of the manufacturing process itself, where you're giving feedback to the designer from the manufacturing process, so that you can design better circuits and better yield and better reliability. So it is very important, it is essential that when you are designing even a simple circuit or a device, you make sure that you understand the limitation of your lab or your fabrication facility, so that whatever you design could be fabricated. Otherwise your design is not going to be realized. So design for manufacturability is one word, or manufacturing or manufacturability. So people tend to also use the other term called technology aware design, right, which is also the same idea. So you are designing your circuits or devices based on the technology. Okay, so just not designing based on the application, but based on whether you can realize this. So this brings us to the end of the brief overview of design for manufacturability. So as I mentioned, design for manufacturability is a very broad area. So what I try to do in this short overview is to create awareness about what are all the places you could expect this variability, what type of variability that you can expect, both in terms of spatial and temporal, and sometimes both spatial and temporal together. And there are limitations from the manufacturing process, right? So one need to understand those limitations and design accordingly, right? So it is possible to design a suboptimal device that has high yield than a best device where you have very poor yield. Okay, this is something that one should be aware while you are designing. So make sure that you understand the manufacturability before you venture into manufacturing a design that you have done.